the previous videos, we have discussed about the long-term losses, which include the shrinkage loss, the losses due to the relaxations of steel, and as you know, for the long-term losses, there is one more component of the elastic and creep loss. In these videos, we're going to discuss about the creep loss and also the long-term losses. This slide presents the equations for us to determine the long-term losses. The equation here represents the simplified method for us to calculate the total losses, which is time dependent. It is by fundamentally the summations of the shrinkage, relaxations, and also elastic and creep losses. If you look into the equation here, you will realize that the equations constitute components of the shrinkage losses, relaxation losses, and also the creep losses. For you to determine the shrinkage losses and relaxation losses, you may refer to the previous video, as we have discussed them separately in these slides. Simply said, if you wish to determine the shrinkage losses alone, you may refer to this slide. And if you wish to determine the losses due to the steel relaxation alone, you can refer to this slide. And if you want to determine the total long-term losses, which is the combinations of the shrinkage, relaxations, and also creep loss, these equations may be referred. Bear in mind that this equation is a simplified approach for us to determine the long-term losses, where there are factors incorporated into the equations to make it more conservative and reliable in predicting the long-term losses. That means if we are calculating the long-term losses, these equations will be sufficient. You do not need to add up again with the losses for the shrinkage and relaxations from the previous video. Now let us look into the components of the equation here. First is the APS. It represents the tendon area, which is calculated by multiplying the number of tendons with the area of each tendon. There are components of the shrinkage losses, relaxations, and also creep. The shrinkage losses is quantified by this. If you refer to the slide of the shrinkage losses, it is calculated by multiplying sigma CS with the EX and APS. This is exactly the three components here that represent the shrinkage loss. And if you refer to this slide here, the relaxation losses is calculated by sigma PR and APS, which is this sigma PR times APS. There is a factor here to modify the magnitude of the relaxation loss. To be more specific, the factor will be this. Since we have discussed these two in the previous videos, for more detail you may refer to those videos. Now let us look at the third components of the losses, which is the elastic and creep loss. It is defined by sigma CQP, which is taken as the average stresses at the support and the midspan. For you to determine the stresses at the support and at the midspan, you may refer to these two equations. The two equations here is exactly the same. The main difference will be there are a component of sigma C external. This sigma C externals is determined by this equation here, which is the external load that causes the moment times E per I. What you see here, the E, I, and A here are all the geometrical properties of the beam section. The A here is not to be confused with the APS here. APS represent the areas of steel tendon. The A here represent the areas of the concrete section. The E here represent the eccentricity of the tendon, and the I represent the second moment of inertia of the section. The M here is determined by its external load. For a simply supported beam subjected to an UDL load, the M caused by the external load will be WL squared per 8. You know that when we quantify the losses, we are normally referring to the serviceability limit state. Therefore, the factor of safety will be equals to 1.0 for GK and QK. The L here represents the effective span of the beam. As you can see from the equation here, if you find it confusing, you can actually use these equations for you to determine the stress in the support. However, for the simply supported beam, there will be no moment at the support. When there is a 0 for the moment here, whichever 0 multiplies with, it will end up to be 0. That's why the stress at the support here do not have this sigma C external. Substitute the relevant value here, you are able to determine the average stress in the member. There is a creep coefficient here, which we're going to discuss later. Let us look into the simpler term first, which are the ES, the modulus of elasticity for the steel tendon, and also ECM, the mean modulus of elasticity of the concrete. This is determined by using this equation, which is in the functions of FCM, governed by the compressive strength of the concrete. The bottom part here represents the denominator for the equation here. There is a factor of chi representing the creep, and there is a phi representing the creep coefficient. The chi here is calculated from the equation here, which is the modulus of elasticity of the steel tendon, modulus of elasticity of the concrete, the total area of the steel tendon, and also the geometrical properties of the section. All this is to be multiplied with the creep coefficient.